Hi guys, in this video lesson, we will be reviewing the exponent properties that you did at the end of geometry and maybe an 8th grade sum. This is the start of the unit that we weren't able to finish due to the state shutdown 2 years ago. So try not to overthink these properties. It is heavy in notation, but we're going to just try to break it down piece by piece, and hopefully that will help you keep track of the different properties. So product of powers property says if you have the same base and you're multiplying two expressions, you can simply add the exponents to figure out the new expression. So let's do it with some numbers and see if that helps. So let's say I were to give you x to the third times x to the fifth. So x to the third, remember, is really just x times x times x. And then x to the fifth is really x times x times x times x times x. And if we count them all up, we get x to the eighth. And this visual is great to see, but when the exponents become larger and larger, it's really nice to remember the rule that if you have the same base and two expressions are being multiplied, you can simply add the exponents to come up with a simplified expression. So here's another example. In this example, we have several pieces. We have the coefficients in each expression. We have the x variable parts of each expression. And then we also have the y variable parts. I'll just underline those are hard to see. So that's how I take things a piece at a time. I'm going to say, well, 2 times -3 is -6. Learned that a long time ago. And then I'm going to say, well, x to the third times x to the fourth, since they have the same base and they're being multiplied, that's simply x to the seventh. And for the next part, y times y to the seventh, well, if I have one y and 7 more y's and they're all being multiplied, I have y to the 8th power. And that's the answer. Quotient of powers property has to do with division, right? Remember, quotient is the solution to a division problem. So let's say I had x to the nth over x to the nth. If I have the same base and I'm dividing, I can simply subtract the exponents. So for instance, let's say I gave you x to the 7th over x to the 2nd. If I were to draw all this out, which would take a minute, and that's okay, I would have 7 x's on the top, 6, 7. And then I would have 2 x's on the bottom, denominator. And if you think about any number, 2 divided by 2 is 1, 10 divided by 10 is 1, 100 divided by 100 is 1. So that also works here when we're talking about variables. X over x divides to 1. X over x divides to 1. So what we're really left with is 1 times 1 times x times x times x times x times x. X to the 5th. This is a good way to prove why, if you have the same base and you're dividing, that you can simply subtract the exponents. So let's look at another one. Again, this expression has more. You have the 4 and the 8. You have the x to the 5th and the x. And then you have the y to the 6th and the y to the 7th. So if I were to break this down, I'm going to start by saying, well, 4 divided by 8 is a half. That's not new to exponents. But if I have 5 x's in the numerator and 1 x in the denominator, then one pair is going to divide out x over x equals 1. So you're left with x to the 4th. Which makes sense because you have the same base and you're dividing, So you can simply subtract 5 minus 1. As far as the y's go, if I were to write out 6 y's being multiplied, because that's what exponents are, repeated multiplication, and then 7 in the denominator, then you're going to have a whole lot of pairs of 1s. Divides to 1, divides to 1, divides to 1. So really what you're left with is 1 times 1 times 1 times 1 times 1 times 1 all over y. So you can simplify this down to x to the 4th over 2y. Now we're going to talk about a power of a power property. Power of a power property says that if you have a specific variable being raised to a power and then raised to a power again, that you can simply just multiply those powers to get your result. This is probably the hardest one to see without seeing something written out. So let's use some variables combined with numbers. Let's say I had x to the 2nd to the 3rd. Well, really what this is it's 3 sets of x squared. And I know each x squared is really just x times x. So I'm left with 1, 2, 3, 4, 5, 6 x's, x to the 6th. And yes, 2 times 3 equals 6. This long expanded form proves why you get x to the 6th when you do an exponent like this. So in this problem, we're going to break it down again like we did in the previous ones. We have negative 5 being raised to the 3rd. We have j being raised to the 3rd. And we have k to the 6th being raised to the 3rd. So we really have 3 sets of this inner expression right here. We've got 3 sets of those. So I really have negative 5 times j times k to the 6th times negative 5 times j times k to the 6th times negative 5 times j times k to the 6th. And I'm going to treat numbers like I've always treated numbers. Negative 5 times negative 5 is 25 times negative 5. Does anybody remember what 5 to the 3rd is? Yeah, it's 125. So you're going to end up with negative 125. And then if you look at the j's, you have 1, 2, 3. J times j times j. So j to the 3rd. And then you look at the k's. K to the 6th times k to the 6th times k to the 6th. Now I could write out k to the 6th times k to the 6th times k to the 6th in expanded form, but it's going to take a really long time. So you're going to be better off just using that property that says, okay, if I'm multiplying with the same base, I can add the exponents. Another way you could look at it is simply to say, well, negative 5 to the 3rd is negative 125. J to the 1st to the 3rd is j to the 3rd. And k to the 6th to the 3rd, we just multiply those exponents and we would get k to the 18th. So this property is called the zero exponent property. So time and time again, kids just kind of forget why anything to the power of 0 is 1. Or maybe you just were never told. Either way, we're going to kind of prove it here. So this is what we're going to say. I'm going to make a nice little list. And we'll just use 2 as our base. So we're going to set it up like this. 2 to the 0, 2 to the 1st. And we know that math is cyclic, that it follows patterns. It's not haphazard. So we should be able to make a table and see the pattern being formed. So let's start over here in the positive end of things. I know 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, and 2 to the fourth is 16. I'm just multiplying by 2 each time. So if I multiply by 2 going up, I should be able to divide by 2 going down. So for instance, 16 divided by 2 is 8, 8 divided by 2 is 4, 4 divided by 2 is 2, 2 divided by 2 is 1. And then 1 divided by 2 is a half, a fourth, a third, oops, not a third, sorry, an eighth, and a 16th. And this works with any base value. And this is the proof as to why anything to the power of 0 equals 1. So let's try a few. So if we look at this first example, 7, everything, the whole parentheses, is being raised to the power of 0. And I know anything to the power of 0 is 1. Not much work to be done. Now down here, you got to be careful because only this part of the expression is being raised to the power of 0. So this part of the expression does become 1, but you have negative 5 times 1, which is negative 5. Now, negative exponent properties. The negative exponent property tells us that if an exponent is negative, if we switch the position, either numerator to denominator or vice versa, that we can make everything into positive exponents. And this always made sense to me because I grew up in northern Michigan and we had lots of negative degree days. And I knew that on a temperature thermometer, negative is way down at the bottom, that it kind of switches the position of that degree mark from something in the positives to something much colder in the negatives. So let's start these by just rewriting them without any negative signs. So I'll leave the x squared up here because it's already positive. And I'll leave the y to the fourth down here because it's already positive. But the y to the negative third, I'm going to move to the denominator. And the x to the negative fifth in the denominator, I'm going to move to the numerator. Positive numbers. So now you can just say, okay, x squared times x to the fifth is x to the seventh. Y to the fourth times y to the third is y to the seventh. And I cannot simplify anymore because I have a single x-based expression and a single y-based expression. I'm done. So let's look at this next one down here. Again, we have multiple parts. We have our parts based on just numbers. We have another part based on x bases and another part based on expressions with a base of y. So let's start with the 10 over 4. Well, 10 over 4 reduces to 5 halves. And yes, you could make that 2.5, but it's kind of ugly with a lot of the exponent properties. So I'm just going to go ahead and leave it as 5 over 2. I'm going to leave my x squared in the numerator because it's positive, and my y cubed in the numerator because that exponent is already positive. But the x to the negative fifth, I'm going to move on up, and the y to the negative fourth, I'm going to move on up. So when I go to break this down, I have a 5 in a numerator, I have x squared and x to the fifth in the numerator, so x to the seventh, and then I have y to the third and y to the fourth in the numerator, so I have y to the seventh, and then everything is over 2. So these are all the exponent properties without coefficients, all the ones that we discussed. And these are those same properties, but this time written with coefficients, with constant multiples. And I will be posting this slideshow on Google Classroom, so you can refer back to it as needed.